Hello everyone. So this is the third lecture of thermodynamics, and in this lecture we'll discuss about first law of thermodynamics and its application. Okay, and before that we'll discuss some of the topics, some of the concepts. Then we'll start first law of thermodynamics, and then we'll do its applications in different types of thermodynamics process. Okay, so first of all, connecting you from the last session, we discussed about adiabatic and isothermal process. So in adiabatic process, we saw that PV raised to the power gamma is equals to constant. For isothermal, PV is equals to constant. Okay, but there is something which we say like this. Now, if you will see just the nature of PV curve in both the cases, you will see similar to hyperbolic curve. But if uh, both adiabatic and isothermal's PV curve is drawn, how will identify that which one is adiabatic and which one is isothermal? So this example, this is a PV curve. This is a point of intersection of adiabatic and isothermal process. One of the curve represents adiabatic, one of them represent isothermal. Now, if we see the point of intersection, then the graph which is above, in which term you can say in terms of, you can say this axis, this volume axis, which is at uh, before point of intersection, this and this, these are two portions of graph. Now this is above as seen from the volume axis. So this will be adiabatic, this will be isothermal, and hence it continues. Okay, you have to understand this. Sometime it is been asked in paper that just identify adiabatic and isothermal process in the graph. So this way you can identify. Now talking about some more things like degree of freedom. Okay, so degree of freedom is the number of independent ways in which we can express or represent the motion of gaseous molecule, right? So this is denoted by small f, degree of freedom. Okay, now it is different for monatomic gas than diatomic gas and triatomic gas. So let us discuss about it. Before that, some terms, that is Cp, Cv, gamma. This gamma is called adiabatic constant, as we discussed earlier. This Cp is molar specific heat at constant pressure. This is the same at the rate constant volume. And this gamma is represented as the ratio of Cp and Cv. Okay. Now, just try to understand. This gamma is adiabatic constant, and it depends. It mainly depends on degree of freedom. How? There is one relation. Okay. There is a name. I'm just forgetting the name of the relation. But the relation is like this: CPM minus CVM. Mayer's relation. Yeah, I remembered. Mayer's relation. It is called Mayer's relation. With the CPM minus CVM is equals to R for 1 mole. Okay, I'm representing the 1. Generally, we write Cp minus Cv is equals to R. It is not, you can say, wrong, but it is when we consider 1 mole. Generally, we consider 1 mole, so we write this. But actually, the more generalized, or you can say more correct way which this is one case, okay, when number of moles is 1, but number of moles when there it is not 1, it is like Cp minus Cv is equals to Nr. So remember this for 1 mole, this is for n moles. I think you got this. Now how gamma? So gamma is simply a Cp by Cv. Now this Cv in terms of degree of freedom it is Fr by 2. Okay, now Cp you know that is Cv plus R by Cv, 1 plus R by Cv. Just write Cv, you will get this like this, Fr by 2, and it will come as gamma is equals to 1 plus 2 by f. So it is depending on degree of freedom. If we change degree of freedom, the adiabatic constant, the value of adiabatic constant will change, and it is in unitless quantity and dimensionless also. Okay, so now what we have to discuss, Cv we have discussed, Cp are discussed. Okay, degree of freedom. So for monoatomic gas we have degree of freedom, we have Cp, we have Cv, and we have gamma. For a diatomic gas, different case. For a triatomic, in next page we will discuss. For monoatomic, remember degree of freedom is 3. See, there are 3 types of degree of freedom: translational, rotational, and vibrational. Vibrational is at high temperature, okay, and rotational and translational will not be at high temperature, that will be at normal temperature or room temperature. So here these 3, the degree of freedom is 3, it means these 3 are the translational degree of freedom, TDOR. Okay, now you will write CPCB 3R by 2, 5R by 2, gamma will be 5 by 3. Now for the diatomic it will be like 3 plus 2, where we'll have 3 degree of translational degree of freedom, and 2 will have what you say, rotational degree of freedom. For a diatomic gas that will be 5, it will be 7R by 2, and it will be 5R by 2, and it will be Cp by Cv, that will be 7 by 5, 1.4. Okay, now talking about triatomic gas. So in case of triatomic, we have 2 cases. First is linear molecule, and second one is non-linear molecule. Okay, now it's your duty to write Cp, Cv, and gamma. I'll just tell you the degree of freedom. Linear molecules like CO2, degree of freedom will be 5. That will be same as the diatomic gas. All are taken at a room temperature, low temperature. We have not considered the high temperature, otherwise we will add vibrational mode of freedom, and that is 2. One vibrational mode of one vibrational mode means 2 degree of freedom, and vibrational degree of freedom is different thing. Vibrational mode, if I am saying, remember sometimes we use the word vibrational mode, it means you have to add 2 degree of freedom, that is a 2 vibrational degree of freedom, right? VDOF. For non-linear molecule we have 6, and that is one of the example is NH3 H2O you can take. Okay, so this is the basic idea which you must have, then we can proceed to the further concepts. Okay, now talking about work done. As you know, work done is a what, a scalar quantity. Okay, it is a scalar quantity. You know this work done is integrand f dot dx, right? I hope you know this, right? Now just you have to do simply that you know one thing also, pressure is force per unit area. So you can write force in terms of pressure as you can write P into A, right? So it becomes like this, P into A dx. Now this A dx becomes dV, that is the volume. This is a way you can express it. So it is like this, P dV. But here we will have a minus sign, here we will have minus sign, and we will have minus sign. This minus sign actually represents that work done is by a system. What is by the system, what is on the system? Let me clarify you by making aware about the sign convention, right? Suppose this is a system. We discussed about system and surrounding in our first lecture of thermodynamics. So system, this is a system. Now if you can say work is done on the system, we will take it positive. If work is done by the system, we'll take it negative. If heat is added to the system or provided to the system, we'll take it positive. If heat is extracted from the system, we'll take it negative. Okay. If temperature increases of a system, then we will take into change in internal energy as positive value. If temperature decreases of system, then we will take internal energy change uh, negative, right? This is the sign convention, which is very useful when you solve numericals, when you understand the concepts. It's very, very important thing. Okay, I hope you got this. Now we will discuss about what you say, some terms like internal energy and heat exchange. Okay, internal energy is a parameter. It isn't obviously, it is energy possessed by the molecule only, and it is something it is denoted by U. Okay, and it depends on temperature. Actually, absolute internal energy is not defined. We define change in internal energy of the system, that is defined by delta U, and that is given by NCV dt. And here delta is there, so we leave it delta T. So from this we can say that internal energy depends on uh, temperature if number of moles is constant, and we are given with a particular gas which will have a particular degree of freedom and particular value of CV also. So in that case we can write that, and we can say that is a more general case, that we can say that internal energy depends on temperature, right? Now talking about heat exchange. Heat exchange means heat absorbed or heat released. It is denoted by small q. Okay. Now this is small q, or you can say delta q, can have three values. It can be zero also. Even delta u can also be zero. There is no issue. Delta u can be positive, negative, zero. No issues. I'm talking about heat exchange because it is more important quantity to understand. It can be NCPDT also. It can be NCVDT also, and it can be zero also. For zero, it will be an adiabatic process, which we'll discuss. This is at the rate constant volume. This is at the rate constant pressure, right? But always remember, internal energy change will be NCV sorry, delta T in all cases. All cases. This formula is applicable in all cases. Whether it is isobaric process, whether it is isothermal process, whether it is isochoric process, in all processes this formula is valid. Quite easy also to understand the change in internal energy. Okay, we have discussed the basic terminology which will give rise to the first law of thermodynamics. Okay, so talking about first law of thermodynamics, that is FLOT, we write in short form first law of thermodynamics. It is, we are talking in chemistry, so don't confuse it with physics. We are studying in physical chemistry. It will be du is equals to dq plus dw. Okay, okay, this you have to understand. In physics, we write dq is equals to du plus dw because there we consider work done by system as positive value. Here we'll consider work done by system negative, as discussed in the sign convention. Okay, so remember, this is our first law of thermodynamics. We'll use it and find the different cases we'll apply it. Okay, so this is the first law of thermodynamics. First you have to just absorb this formula, absorb this equation, that du is equals to dq plus dw. It means it is saying us that if we are concerned with the work done, then change in internal energy minus how much heat exchange is there. If we'll just subtract these two quantity, we will get the net work done. Okay, and we can verify it with the generalized formula of work done also. Okay, generalized formula I discussed earlier, that is integrand PdV. We will use that also. So let us start understanding the applications of first law of thermodynamics in all the four processes, that is isobaric, isochoric, isothermal, and adiabatic process. Okay, let's start with isobaric process, a most fundamental process, isobaric process. Here pressure is constant. dp you write, or delta p you write, it is zero. Okay, this dp, delta p, d is representing differential, delta is a big change, delta represent a little big change, d represent a small change. We have different operator in mathematics we use, like Hevelation operator, which we will use to represent total energy of, that will be in quantum physics, we will discuss this operator, that is, you can say, uh, the inverted triangle. This is called Laplacian operator. We'll discuss about it. But right now you have to understand that these two are the operator, mathematical operator, which we use here. So as pressure is constant, we know differential will be 0. Now, talking about using the what you say ideal gas equation, PV is equals to nRT. Now, taking the differential, PdV plus VdP is equals to nRD delta T. Your DTU, right? Now, pressure is constant, so this term will be vanished and will be 0. Now PdV will be equals to nR delta T. This one relation you must know. PdV is equals to nR delta dt. And right here. Now talking about what you say heat exchange. So I already explained you that it will be NCP dt, right? dq for constant pressure. Du will be always NCV dt. Now just use the first law of thermodynamics to find the relation. Du is equals to dq plus dw. How we can find dw? Du minus dq. That will be NCP NCV dt minus NCP dt NDT CV minus CP, and just write the CV minus CP as minus R, as we know CP minus CP is R, so CV minus CP will be minus R, so minus NR dt. So dW will be minus NR dt, and just we discussed NR dt is nothing but PdV, right? So minus PdV, this is our work done. And even if you use the generalized formula, that is this, just taking the pressure constant and taking out of the integration, it will be like this, and V initial to V final, it will be like P delta V. Okay, D changes to differential changes to delta, and we can write this as minus of P V final minus V initial, and it will be P into V initial minus V final also. Got it? That's as simple as that. This was our concept of isobaric process. Now talking about isochronic process. Graphs I already discussed with you in the last session. So isochronic process we will discuss now. So let us go differently now. Now we'll use the definition of work done, and we will then find another quantity. Just we have to make some interest. Okay. Isochronic volume is constant. dV is 0, delta V is 0. No issues at all. Right? Now here we can write PdV plus VdP is equals to nRdt, and here this quantity will go 0 and VdP is equals to nRdt. Okay, this is possible, written. Now work done as per the definition. Let's write now minus. Okay, there I used minus or not? I think I used or not. You just check, and I can't go by backslide. Okay, you may check. This minus is important. Okay, this minus is important. It will be there. Okay, so just check it out. Okay, if I made mistake, then I'm sorry for that. It might be. Okay, I can't check right now. Okay, so you can check. This minus is important. It is representing the work done by system. Okay, so minus dv is 0, so the work done will be directly 0, right? Now du is equals to dq plus dw according to first law of thermodynamics. That is coming 0. Du will be equal to dq is equals to ncv dt. Directly we did this. So easy, yeah? You must have the control on this topic, that you can write by your own that what are happening in this process. This is a very beautiful thing. You just write isobaric, you write pressure constant, you write differential 0, and then you proceed to find the expressions of work done, heat exchange, and internal energy. Okay, now this was our isochronic process. Third one, isothermal process. One thing I want to clarify you. See, my lectures are very short, or you can say 20 minutes, 25 minutes, maximum 30 minutes, except the lectures on physics. Okay, in physics we take lectures little lengthy, but here lectures are around 30 minutes, 35 minutes maximum. 35 minutes is maximum for me. But you see the contents are very the content which you get in 1.5 hours, if I'm giving you in 30 minutes, that's not something can be used, because I'm giving the crux. I'm giving the crux idea. I'm not using any PPT. I'm not using anything. I have made a separate class for problem solving, challenging discussion. So little different way of my teaching and is of my uh, making clear with the concepts. Okay, but the concepts are these are. For isothermal process, temperature is constant, dT is 0, delta T is 0, and you remember delta U is equals to density V delta T, so it will be also be 0. Now, for temperature constant, PV is equals to constant. Okay, done. Okay, means pressure is inversely proportional to volume. We can write P1 V1 is equals to P2 V2. If this P1 V1 represent initial pressure volume, this is final pressure volume. So we can write here P1 by P2 is equals to V2 by V1, and this is also clarifying this also. So simple it is. Now, work done. This is a generalized formula. Now you know PV is equals to constant, that is nRT. We will write pressure in terms of temperature, volume, and the constant parameters. Even temperature is also constant here. In terms of constant parameter and volume, we can write pressure, right? What we'll get? Minus integrand nRT by V into dV minus nRT. This dV by V integration will be ln V, that will go from V1 to V2. So V1 to V2 minus nRT ln V2 by V1. Just use a one step more step. You can use ln V2 minus ln V1, and then you can use the logarithm property. Okay, basic logarithm. I think you know. Otherwise, I'll have to take the class on basics of mathematics required for chemistry. So I don't want to take that. I expect from you that you know the basics of mathematics. Okay, ln V2 minus ln V1. Here it will be. Okay, and you can write that in this way, and you can represent it in pressure also, as I discussed that you can write it here like this, ln P1 by P2. This is also correct. Both are interconvertible. Okay, so this was our isothermal process concept of work done. Now, talking about the first law of thermodynamics, it is 0. We can write dq as minus dw. Just use this expression and just use, you have to just find work done and you have to just apply a negative sign with it. You will get the heat exchange in the reaction whole process. Okay, reaction process. Now, last process, we have adiabatic process in which heat exchange is 0. Okay, temperature is not constant here. Remember, here temperature is not constant. Don't get confused by this. Temperature is not constant. Okay, so Q is 0, and we have du is equals to dq plus dw. So whatever you will get the expression of du, that will be the same expression you will get for dw also. Since it is an adiabatic process, here it will not go very simply. So PV power gamma is equals to constant. Like this the expression goes. The work done we get here as minus nr delta t over 1 minus gamma. This you have to remember. And work done is equals to minus nr delta t by 1 minus gamma. Or you can write it as minus P final B final minus P initial V initial over 1 minus gamma. Clear? This will be the expression of work done, and in this way you can find the du value of du also here. Okay, so this was your adiabatic process. Okay, and I discussed with you the three forms of adiabatic: PV power gamma constant, TV power gamma minus 1, and one more that we discussed, I think, in as I remember, we discussed in the last session. Okay, so this was our application of first law of thermodynamics in different thermodynamic processes. Okay, graph we discussed earlier, and these are the concepts which you must know. Okay, so this was our today's session. Near 25 minutes we have taken. The concepts are all done. In next lecture of thermodynamics, we will discuss about second law of thermodynamics and a little discussion about third law of thermodynamics. Little, may or may not be. Second law of thermodynamics is important to understand the spontaneity of reaction. We will discuss that. We'll discuss the Gibbs energy, enthalpy, everything at a beginner level, and then last session we'll have a challenging test discussion. This was the very important session. You can say this was the 50% of main thermodynamics, from where the questions are framed. 50% part is 50, 60, 60, 60%, 60% you can say is this. 40% is your second law of thermodynamics and the previous topics which we discussed. Okay, thermodynamic process and its first law of thermodynamics and its application. This is a part which covers 60%, 70%. Okay, 60% you can say, and 40% the remaining portion. Okay, thank you so much. uh, so yeah, thank you for joining me in this session, guys. Okay, so in next session we will discuss about the spontaneity of reaction, second law of thermodynamics, second law of thermodynamics in next session of thermodynamics. Okay, this session you will get our 30th, hopefully 30th you will get, yeah, 30th 4 p.m. Okay, so next session will be on 2nd of May or later on. Okay, so we will discuss about it. Okay, thank you so much, and bye bye, take care, and exiting 1 2 3. Thank you.